Hello, good morning students. So, let us now transition to a new biomolecular spectroscopic technique which is called circular dichroism. Now, this is a very important technique in the structural biology, looking at the drug discovery, its application, quality control for industrial application and so on and so forth. So, CD is widely used and it is widely appreciated as a prominent technique in biophysics. Now, just to recap you, we are talking about electromagnetic waves. So, electromagnetic, that means there are two components, one is magnetic component and one is electric component, and though both are perpendicular to each other, and then wave is propagating in the perpendicular direction to both of these, right. So, in the it is a suppose electric vector is in z direction and magnetic vector is in x direction, the wave propagation happening in y direction, right. So, z, x and y, that is the propagation happens, and you remember from your 12th class physics that this is the wavelength, the distance between two turf or crest, that is the wavelength. So, that is the electromagnetic wave, and in spectroscopy we all the time talk about electromagnetic wave, right. So, you know, like we have talked about little bit of rhodopsin and vision that we had covered in the previous lectures, right. So, we have talked about like a mostly in the case of linearly polarized light, but there is another polarized light that we will be discussing in this week called circularly polarized light, right. So, linear polarized light where electric field oscillates in a single phase like this and phase angles are equal x alpha x equal to alpha I. Now, in circularly polarized light, that is what the difference happened. So, linearly polarized light we have seen in UV visible, the fluorescence and all those. In circularly polarized light, now this electric field rotates at a constant magnitude like this, right, like this and like this, right. So, with a phase difference of plus minus 90 degree. If it rotates plus 90 degree, it is called counterclockwise rotation, that is a left handed circularly polarized light. If it rotates minus 90 degree, it will be called clockwise rotation, right. So, and there is a third kind of polarized light which we can call it elliptically polarized light. So, here electric field actually it ellipse, you know, right, this is where not a circle where the two axes are different. So, long axis and short axis. So, in that case elliptical field it is a arbitrary amplitude and phase difference, and that typically when it absorbs it follows the Malus law where I equal to I 0 cos square theta. So, I is the light that is coming out, I 0 is the incidence light and theta is the angle between polarizer and analyzer. So, we are going to discuss these concepts little more in detail, and we have the like application of such polarized light, like so absorption we have seen the polarization sheet, the dichroic material we put it and the light gets polarized, that we have seen in seed as in the UV visible as well as fluorescence. We have also talked earlier about reflection that follows the Brewster angle, that is theta b about 56.3 for glass well, it is a reflection happening, right. Then we have briefly seen birefringent where the you have a different wave plates, like it can happen lambda by 4 or lambda by 2. Then we have talked about scattering, again we will be discussing all those in detail, little more detail as we come along. And scattering is a important phenomena that is used in spectroscopy, you know, the color of a sky is blue because of a scattering. So, those basic concepts we know it, but in this week we are be mostly concentrating on circular dichroism. Dichroism, right, circular means light has to be circularly polarized and dichroism means two, right, two chroism, two color. So, two colors we are talking about which are circularly polarized light. So, what happens in this case, a chiral molecule absorbs this left handed circularly polarized light and right handed circularly polarized light, and that gives to this wonderful phenomena which is observed in CD, right. So, absorption difference of left handed polarized light versus right handed polarized light we measure in circular dichroism, and that has application in determining the protein secondary structure, which gives the quantitation of an alpha helix or an beta sheet or a random coil, right. So, this gives the idea of how much this chiral center which is in protein, right. So, if you consider all 20 proteins, there is a 19 protein which is chiral like a, and basically proline is achiral, but 18 are chiral amino acid and 2 amino acid has a 2 chiral center. So, that means our protein is a chiral molecule, right. So, chiral molecule they absorbs differently left handed and right handed circularly polarized, and that is what we measure for protein structure determination. So, let us go ahead and look at little more in detail what is happened. So, we will start with a fundamental with this film that where CD is being used and how it is different than other technique like absorption, like a scattering, like a birepresent and all those. So, polarization, right, light polarization. What is polarization and what are the concepts in the polarization? So, polarization describes the orientation and temporal behavior of electric field. Orientation, whether it is x axis, y axis, z axis, what is, and how it is changing, right. So, electric vector, how it is changing of any electromagnetic wave that propagates through space, how it changes, that is what you measure the polarization. So, the key principle is light and is an electromagnetic wave which has 3 components. We know that electric component, the magnetic component, and third one is propagation. Propagation is happening in say z direction. So, we have x and y direction this, and Malus law says that for any polarized light passing through an analyzer, the light that comes out from this analyzer I will be equal to I 0 cos square theta. Now, I 0 is the incidence light and theta is the angle between polarizer and analyzer, and I is transmitted intensity. So, if you look at natural light versus polarized light, these are some of the difference of the property of natural light and polarized light. Electric field in natural light it randomly oscillates in all perpendicular plane. In this polarized light it is confined to a single plane, that is a linear, and if it rotates like this, if we are polarizing the light in a single plane like this up and down, that is a like that is a linear light. If it rotates like left handed or right handed, that will be circularly polarized light. Orientation in natural light, unpolarized light is a multiple orientation with equal probable, wherever they are, all are equally probable, and that basically can orient themselves. Now, in this case circularly polarized light, it has a fixed orientation, it cannot be random, it is a fixed, and it is systematically, if you look at the rotation that I talked to you, either right or left, it is a systematic rotation that is happening. This natural light can come from any thermal source, it can be sun or a bulb like a common tube light or bulb that we have, but for polarized light you have to have a laser, right, and a polarizer or some birepresent material which gives you this polarized light. And intensity it can be uniform in all directions, but here direction determines where the intensity is going to be. So, the use of this polarized light is going to be in a spectroscopy. Polarization matters a lot when we are doing a spectroscopy, especially the topic for this week discussion circular dichroism, right, and which is used for protein analysis. You use this polarized light also for 3D imaging like a 3D movie or even LCD display, where we are putting this slides, the LCD display also use this polarized light. Then you have a telecommunication, it is like a fiber optics signal transduction that happens, signal transmission that happens is also used in this telecommunication. Even in ophthalmology or OCT, optical coherence tomography, use this polarized light, and of course, in protein dynamics we use this polarized light, right. So, how the electromagnetic wave representation happens? So, basically as we know the light is travelling in z direction, there are 2 components, electric component and magnetic component, and these oscillate. So, Ex if you decompose this in Ex vector x direction, you can put it the wave as a function of cos theta, where you have phase angle and the frequency, and y component you can write it there. So, here are the parameters that are there, the wave number, that is 2 pi by lambda, the angular frequency which is omega, and phase angles alpha and beta, and these are the E x and E y are the amplitude of that. So, if you just go back, this is the way we are trying to write it mathematically, that we discussed about this. So, we are, if we write it mathematically, the wave E x and E y, something like that, right. So, the phase difference, like two waves, one wave is going like this, if they are on top of each other, that is there is a 0 phase difference, but if they are just one is lagging and one is leading, then you have phase difference. So, that is x y component determines the polarization state. So, delta is suppose phase difference, the E y and E x, E y and E x determines the phase difference. So, if there is a phase difference is 0 or 180 degree, 0 like on top of each other, or 180 degree like the other goes. So, 0 that means one and another here, 180 degree that means here it has crossed one and then second starts. So, that is a 180 degree. So, 0 and 180 degree, this will be a linearly polarized light. So, here the E vector oscillates along a single line, if you look at where we are oscillating in a single line. But if the phase difference is 90 degree, means one is going like this and then another, here the first one and then another starts. So, that is a 90 degree. So, that will be circularly polarized light. So, that means our E vector is rotating in a circle, right, it is rotating in a circle. And if this delta any other angle, like a elliptically polarized light. So, if suppose one has reached here and another now starting from here. So, that means the two E x and E y are not going to be equal, and in that case it is a elliptically polarized light, right. So, that is a polarization. So, if you look at here, in this case electromagnetic wave travelling in z direction has an electric component E z t, that means travelling in z direction at any time t, this is the electric vector. It has a E x component and E y component, and these are the phase angle. So, if one is going in this direction, that is a right handed polarized light, another is going in opposite direction here, that is a left handed polarized light. That is what we are talking about, phase difference of E x and E y by 90 degree, right. So, polarization state can be described using Jones vector, right. So, these are the J vector, this is a mathematical notation allows the calculation of light polarization after passing through optical polarizer, right. So, we talked about that in the previous slide, if phase difference is 90 degree, that will give us a circularly polarized light, because light is now rotating in an angle, right. So, linear light, that is a plane polarized light, single plane oscillation. In linear polarized light, electric field oscillates in a single plane like this, right, and in circularly polarized light, one is right handed, another is left handed. So, here you have type of horizontal line where E y equal to 0, E x not equal to 0, then angle from horizon is 0 degree, it is a horizontal transmission line. Vertical, E x will be 0, E y not equal to 0, that is a 90 degree and vertical transmission line. The diagonal where E x and E y both are not equal to 0 with equal amplitude, that is a 45 degree case. And then arbitrary angle, you can have E x not equal to 0, y not equal to 0, then theta is some angle like a tan theta, you can have it E y by E x, that is a customized orientation of these lights. So, we can have different kind of polarization, right. So, that we can write it, the electric field z direction is going, and you can see this is light is oscillating, and you can have a linearly polarized light, something like that. So, you can write it the straight line where theta you can have E y by E x. If it is 45 degree, you can put it all the value and get it the 45 degree. Now, intensity of the linearly polarized light, you can write it I equal to 1 by 2 E 0 E x square plus y square, and one can calculate the intensity. Now, the generation of linearly polarized, how we essentially generate it, right. So, as I said, we start with unpolarized light, we put something here, a polarized film, polarized film, and when this light goes, it gets linearly polarized and follows this Malus law, I equal to I 0 cos square theta. So, method is you are first putting absorption, the light is getting absorbed, that is happening by polarizer sheets. We are putting a polarizer sheets here, and what is happening? We are using the dichroic material. Dichroic means two light is getting differentially or unequal absorb of perpendicular component. So, if they are unequally absorbing the component, then what happens, that it goes in one direction. So, light contains say iodine molecule or a polymer. Now, what happens, absorbed light like here E vector parallel to the molecular axis, transmitted light is perpendicular to the axis. So, transmission that is happening, parallel component almost goes to 0. So, one of the component parallel one going to 0 and perpendicular component passes through it, 50% gets passes through on 50% of unpolarized light. So, then what we results into linear polarized light perpendicular to the molecular axis. You can see here now we have the started with unpolarized light and we have a material which is polarizer that is unequally absorbing it. So, one component gets absorbed and whatever emits only 50% of the incidence light according to this formula that we talked about, and what we achieves is a polarized light. The another way we can make it polarized light by this something called reflection method, which follows this Brewster angle. So, here the specific angle at which reflected light becomes the linearly polarized, right. So, how it happens? So, we have to, like, you remember the water and air interface, similarly we can have a reflection something like that. So, you have to have a specific angle where light gets reflected, and that is given by this tan theta b, where these are the two refractive index for glass air interface, that theta b is 56.3 degree. So, at this Brewster angle, which is 56.3 in this air glass interface, the light polarized parallel to the plane of incidence and you have a 0% reflection, and light polarized perpendicular to the plane, maximum reflection happens, and that gives you the linearly polarized light. So, to get the linearly polarized light, what you need? And source, you need a polarizer film and some physical parameter, physical formula which tells you how much light is going to come, either by absorption method or by the reflection method. Essentially, by doing this we can get the plane polarized light, right. So, now generation of linearly polarized light we can get by this birepresent. Birepresent is the third way. So, we take a birepresent material where refractive index perpendicular to the polarizer. So, we can have a material something like quartz, which is made up of silica oxide or calcite or mica. They have extraordinary refractive index and ordinary refractive index, and they basically, when this light passes through the birepresent material, you have the polarized light. So, here using quartz, like quartz already we talked about when we were discussing about UV visible or fluorescence, you have the UV visible polarizer. In calcite you have polarizer prism like a CaCO3, and when mica sheet we have a wave plate and recorder. So, basically what we are doing, wave plate function is to introduce a phase angle. So, you will see this is a phase angle that is getting introduced, and we can have a different kind of phase angle. We can have a lambda by 4, that is a 90 degree converts linearly to circularly, and if we have 180 degree phase that rotates, it rotates the linearly polarized light. So, we can choose basically the birepresent material which will convert even a linearly polarized light to circularly polarized light or linearly polarized light in opposite, like a different direction, 180 degree phase shift. So, see, first we can make the unpolarized light to polarized light, and then also we can change the polarization from linear to circular, that is what we see. Now, that is a generalization of linearly polarized light. So, what we do, the fourth one again it is a polarization method. So, we talked about absorption, we talked about, if you remember, we talked about first is absorption, second is reflection, third is birefringent, and fourth one is scattering. So, scattering, it is a typically polarized scattering happens perpendicular to the incidence light. So, and follows that lambda by 4 rule, and that is why sky is blue, right, we all this see. So, one can have a scattering method where you can have the input intensity I 0 and after polarization I by 2, 50% transmission loss, and by scattering again you can get the light, polarized light. So, these are the 4 way we can have it. Now, what are the characteristics of this linearly polarized light that we prepared by all these methods? So, key characteristic that one can have is single plane oscillation, since it is a linearly polarized light. So, it is oscillating just in single plane. So, electric field oscillates in one plane like this and it propagates in z direction. Now, magnetic field oscillates perpendicular to the plane, both perpendicular to the pop. So, it is just oscillating in this direction, right, that is the propagation angle, and this is a fixed angle. So, that means whatever orientation angle is constant, it is propagating with a theta equal to constant. And phase relation, here the phase, the both phase, like a phase of the wave alpha x equal to alpha y. So, both reaches maximum and minimum simultaneously. So, this is the first one, and the second one, if it is happens maxima and minima, that is a like a constructively moving, and that is the relation, that is a key characteristic for linearly polarized light, right. So, we can have mathematical notation, one can have Jonas vector for propagation, and that is what we can have for the linearly polarized light more or less, right. So, transmission, if it is happening through optical element, the linear polarized light input is unpolarized, we can phase shift, we can select depending upon absorption, and it is a linear perpendicular direction. If you have a linear polarizer and input is linear at theta angle, absorption happens by Malus law and linear at the theta angle. If we have a full wave plate for the optical transmission, it will be linear at theta angle and then phase shift is 360 degree, again it is a linear. If we have a quarter plate, that means linear 45 degree, phase shift happened by 90, and then we can get this circular one. If we introduce half wave plate, that is linear at theta degree, we have a phase shift of 180 degree, that will be linear, but minus theta angle, right. So, all these possibility we can generate linearly or circularly polarized light, depending upon what is the polarizer, what is the intensity, and how we can get the different intensity. Now, the circularly polarized light, here we are rotating the vector, right, rotating the electric vector. So, in this case, the light where electric field vector rotates at a constant magnitude, we are rotating, basically this vector is rotating like this, and that is why it is circularly polarized light, right. So, we can rotate these vectors to generate a circularly polarized light at constant angle. So, here the important point that in circular polarization we have a equal amplitude, E x equal to E y, that is E 0, there is a phase difference of 90 degree, that lambda equal to E y minus E x, that is plus minus 90 degree, and we have a resultant electric field which can be given as E 0 cos like a k z omega t x plus sin k z omega t. Magnetic behavior is for this case, now for circularly polarized light it is a fixed one. So, you have a constant value, right, magnetic behavior is constant. In this circularly polarized light, we have two kind of polarization. One we talked about right handed polarization and another we talked about left handed polarization. So, in right handed polarization, the shift is minus 90 degree, that lags by 90 degree, and here for viewing we can see it is rotate clockwise. E, the wave when viewing from along the propagation, it rotates counterclockwise like this, and right handed rule, the thumb points the along propagation and then these the fingers that says the rotation. In the left handed polarization light, the phase difference is plus 90 degree. So, y leads x by 90 degree, y is leading by x. So, now if we view towards the source, the E vector rotates counterclockwise like this, and E vector when propagation we see it rotates in the clockwise, and here again we have a left handed rule. So, thumbs points along the propagation, finger calls about the rotation. So, that 12th class rotation that we have seen, but here briefly it is a clockwise rotation and here is a counterclockwise rotation, right. So, circularly polarized light we can have a linear right handed, left handed. So, E prime is linear, here its versus time we can put it, and we can have this 0 on 180 degree, here minus 90 degree phase shift, here plus 90 degree phase shift, no rotation happening. This is if you are viewer with clockwise rotation happening, this here counterclockwise rotation happening. And Jonas vector here one can have cos theta, sin theta, and you can give it the intensity that is coming out, and this is basically one can put it in this matrix to find it out how much intensity is coming out. So, electric field tip trajectory we can have looking perpendicular to the propagation, and one can find it out what is the electric vector rotation in the clockwise or counterclockwise for left handed and right handed polarized light, right. So, one can basically it is just a 12th class recap that one can go and read it, what will be the propagation, what will be intensity, and how this polarized light comes. So, essentially to sum up this is a counterclockwise rotation that is happening here for the right handed clockwise rotation, here it is a left handed the clockwise rotation happens like this, and left hand rule one can have mirror image, right hand rule we can have something like this, right. So, this is the right handed and left handed polarized light that one can have it in this case. So, if I sum up what we discussed, that for this spectroscopy the important component is having a light which is polarized. It is not a linearly polarized, but a circularly polarized light. Circularly polarized light can be generated by putting some manipulation in the light propagation, manipulation like it, if you put something which can absorbs, which can like a which can reflect or birepresent or scattering, we can generate this. Now, how much light is going and how much light is coming, it can be given by mathematical operation. What will be the rotation of these depending upon how E vector rotates, those we saw it. So, essentially for doing this kind of a spectroscopy you require your plane polarized light to broken into two component, one is right handed, another is left handed, and you require a molecule that can absorb this right handed and left handed differentially. So, typically what we discussed, a chiral molecule basically will absorb these left handed and right handed polarized light differentially, and this technique that we are going to talk today, the circular dichroism, will be essentially measuring the difference of left handed polarized light and right handed polarized light, and that gives you idea about the secondary structure of the protein. So, with this basic concepts of the wave propagation and generation of light, we delve deeper into how are we going to use this concept to understand the differential absorption by a chiral molecule. So, let us end it here and we look forward to have you in the next lecture. Thank you very much.